The moment an urban system begins to fail, movement becomes the most dangerous decision you will make. Not because escape is impossible, but because the city is not designed to let large populations move efficiently under stress. What appears on a normal day as a network of roads, transit lines, and pedestrian pathways is, in reality, a tightly optimized system built for routine flow, not emergency evacuation. When disruption hits, whether from power failure, infrastructure damage, or systemic collapse, the same pathways that once enabled mobility become choke points that trap movement. The danger is immediate, but it is also deceptive because the instinct to flee is often stronger than the understanding of how movement actually works under these conditions. To analyze this, you have to understand that cities operate on predictable patterns of traffic density and flow distribution. Roads are engineered based on average usage, not maximum surge capacity. During peak hours, many urban systems already operate near their limits. When an unexpected event triggers mass movement, demand exceeds capacity instantly. Vehicles accumulate faster than they can disperse, intersections lock, and minor disruptions cascade into full gridlock. This is not a failure of individual drivers, but a systemic overload where the network itself cannot process the volume of movement. The result is immobilization at scale. A common misunderstanding is that having a vehicle guarantees mobility. In reality, vehicles become liabilities in high-density collapse scenarios. They require space, fuel, and functional road networks. When any of these variables fail, the vehicle transitions from an asset to an obstacle. Stalled cars block lanes, reduce maneuverability, and create physical barriers that restrict alternative routes. The assumption that speed and distance can be achieved through motorized transport ignores the constraints imposed by congestion and infrastructure failure. Movement becomes slower, less predictable, and more resource-intensive. The hidden science behind this lies in network congestion theory and nonlinear system behavior. Traffic systems exhibit a threshold effect where flow remains stable up to a certain point, but once that threshold is exceeded, the system collapses into congestion. At this stage, adding even a small number of additional vehicles can cause disproportionate increases in delay. This phenomenon, known as phase transition in traffic flow, explains why roads that appear functional can suddenly become impassable. The system does not degrade gradually, it shifts abruptly from movement to stagnation. Evidence of this can be observed in evacuation events during natural disasters. In multiple documented cases, evacuation routes designed to handle increased traffic still became overwhelmed within hours. Vehicles remained stationary for extended periods, fuel supplies were depleted, and individuals were forced to abandon their cars and continue on foot. These patterns are consistent across different regions and types of events, indicating that the underlying issue is structural rather than situational. The infrastructure simply cannot support simultaneous large-scale movement. The survival implications are critical. Attempting to leave an urban area without understanding these dynamics can result in entrapment in transit, where resources are limited and exposure to risk increases. Water, food, and fuel become inaccessible while stationary, and the environment becomes unpredictable. Remaining in place may initially seem counterintuitive, but it allows for controlled resource management and reduces exposure to the uncertainties of movement. However, staying is only viable if the location can support basic needs over time, which introduces a separate set of challenges. Escalation occurs when delayed decision-making intersects with increasing congestion. Early movement may provide access to less crowded routes, but it also carries the risk of acting on incomplete information. Waiting allows for better assessment, but increases the likelihood of encountering blocked pathways. This creates a narrow window where timing becomes critical, and misjudging that window can eliminate viable options entirely. The environment becomes one where both action and inaction carry risk, and the margin for error is minimal. At this point, the transition shifts from the question of whether to move to how movement should be executed if it becomes necessary. The focus moves away from primary routes and towards secondary and tertiary pathways, routes that are not designed for high-volume traffic but may remain accessible precisely because they are overlooked. Understanding how to identify and utilize these pathways is not intuitive, and it requires a different way of thinking about urban navigation. The next layer of complexity emerges when you consider that these alternative routes are not always visible or obvious. They exist within the structure of the city, but are often ignored under normal conditions. And accessing them requires not just knowledge of geography, but an understanding of how urban systems behave under stress. Right? Next part. As the primary routes begin to fail and congestion locks major arteries into immobility, the city does not become completely static. It redistributes movement into smaller, less visible channels. The danger here is assuming that all pathways are equally affected. In reality, collapse does not spread uniformly. It concentrates along predictable lines of pressure, leaving gaps that are not obvious unless you understand how flow redistributes under constraint. These gaps are what determine whether movement remains possible or becomes impossible. And they exist not by accident, but as a consequence of how urban systems are designed. Analyzing this redistribution requires looking at cities as layered networks rather than single systems. Beneath the visible grid of major roads lies a secondary structure of service roads, maintenance corridors, pedestrian pathways, rail lines, and utility access routes. Under normal conditions, these pathways carry minimal traffic because they are not optimized for efficiency or speed. But when primary systems overload, pressure shifts into these secondary networks. The key factor is capacity relative to demand. While these routes are smaller, they are also less saturated, which can make them temporarily viable for movement if accessed correctly. A common misunderstanding is that navigation tools or prior familiarity with a city are sufficient to identify escape routes. In a collapse scenario, static knowledge becomes unreliable because conditions change dynamically. Roads that were accessible minutes ago may become blocked, while previously ignored paths may open due to lack of usage. Digital navigation systems, if still functioning, may not reflect real-time conditions accurately due to loss of data inputs. This creates a mismatch between perceived and actual accessibility, leading individuals into congested or hazardous areas. The hidden science behind effective route selection lies in understanding flow avoidance and entropy in network systems. When a system becomes congested, movement naturally seeks paths of least resistance. However, human behavior tends to concentrate on known routes, even when those routes are failing. This creates a feedback loop where familiar pathways become increasingly overloaded, while unfamiliar ones remain underutilized. The ability to break this pattern, choosing routes based on structural logic rather than habit, is what creates an advantage in movement. Evidence from urban evacuation studies shows that individuals who deviate from primary routes early tend to experience lower congestion and faster movement times. In contrast, those who remain on main arteries often become trapped in prolonged delays. These findings are consistent across different types of events, from natural disasters to infrastructure failures. The data indicates that the effectiveness of a route is not determined by its size or design, but by its relative usage at the time of movement. The survival implications are immediate. Access to alternative routes can mean the difference between continuous movement and complete immobilization. However, these routes come with their own constraints. They may be narrower, less maintained, or partially obstructed. They may require movement on foot rather than by vehicle. This introduces a trade-off between speed and accessibility, where the fastest path is not always the most reliable. Understanding this trade-off is essential for maintaining progress without becoming trapped. Escalation occurs as more individuals begin to recognize and utilize these secondary pathways. What was initially a low-density route can quickly become congested if too many people converge on it. This compresses the available window for effective movement, making timing even more critical. Delayed access to these routes reduces their advantage, and the system begins to mirror the same congestion patterns seen in primary networks, but on a smaller scale. At this stage, the transition shifts toward micro-navigation, movement decisions made at a granular level, rather than relying on predefined routes. This involves continuous assessment of conditions, adjusting direction based on immediate observations rather than fixed plans. It requires awareness of environmental cues, sound, movement patterns, density of people or vehicles that indicate where congestion is forming or dissipating. Movement becomes adaptive, guided by real-time feedback rather than static maps. The deeper realization is that escape is not a single path, but a sequence of decisions made under constraint. Each segment of movement influences the next, and success depends on maintaining flexibility rather than committing to a rigid route. This is not intuitive because most navigation systems encourage fixed paths. In a collapse scenario, rigidity becomes a liability, and adaptability becomes the defining factor. As movement continues through these secondary networks, another layer of complexity emerges: terrain and structural barriers. Cities are not uniform landscapes. Elevation changes, building density, and infrastructure design create physical constraints that shape how and where movement can occur. Understanding these constraints is critical because they determine not just the direction of movement, but the effort required to sustain it over time. Right. Next part. As movement shifts into these narrower pathways, the physical structure of the city begins to assert control over what is possible and what is not. The danger is no longer just congestion, it is terrain constraint. Urban environments are not flat, open systems. They are layered with elevation changes, enclosed corridors, dead ends, and structural bottlenecks that are invisible until you encounter them under pressure. What appears on a map as a simple connection may, in reality, involve stairwells, locked access points, restricted passages, or gradients that drastically slow movement. The assumption that all paths are equally traversable becomes a critical error at this stage. Analyzing terrain within cities reveals that movement efficiency is heavily influenced by verticality as much as horizontal distance. Bridges, overpasses, tunnels, and multi-level structures are designed to separate flows under normal conditions, but during collapse, they become points of compression. A bridge, for example, may offer a direct route out of a dense area, but it also funnels all movement into a limited width with no alternative exits. If blocked, it becomes a trap. Similarly, underground passages can provide shelter or alternative routes, but they also restrict visibility and escape options, increasing risk if conditions deteriorate inside them. A common misunderstanding is that shorter distance always equals faster escape. In reality, the effort required to traverse a route is determined by both distance and resistance. Resistance includes incline, obstacles, surface conditions, and crowd density. A shorter route with high resistance can take longer and consume more energy than a longer route with lower resistance. This becomes critical when movement must be sustained over time, especially on foot, where energy expenditure directly impacts endurance and decision-making capacity. The hidden science here involves biomechanics and energy efficiency. Human movement under load is constrained by caloric expenditure and fatigue thresholds. Carrying supplies increases metabolic demand, reducing the distance that can be covered before rest is required. Inclines amplify this effect, as climbing requires significantly more energy than moving on level ground. Uneven or obstructed surfaces increase the risk of injury, which in a degraded environment can have severe consequences. Efficient movement, therefore, is not about speed alone, but about maintaining a sustainable pace that balances progress with conservation of energy. Evidence from urban search and rescue operations shows that teams prioritize route planning based on accessibility and safety rather than directness. They avoid narrow choke points, unstable structures, and areas with limited visibility, even if those routes are shorter. Their objective is not just to reach a destination, but to do so without becoming compromised along the way. These principles apply directly to survival movement, where the cost of a misstep is significantly higher due to lack of support systems. The survival implications become more pronounced as fatigue accumulates. As physical energy declines, so does cognitive clarity, increasing the likelihood of poor decisions. A route that seemed viable at the start may become unsustainable halfway through, forcing unplanned deviations. This introduces uncertainty and increases exposure to unfamiliar terrain. The ability to anticipate and manage these factors determines whether movement remains controlled or becomes reactive,